Hello, welcome. In this lesson, we're going to talk about vector functions and space curves. A vector-valued function or a vector function is simply a function of one or more independent variables whose range is a set of multidimensional vectors or infinite dimensional vectors in some cases. The input of a vector-valued function can be a scalar or a vector. In this course, we are most interested in vector functions R of a single variable t, whose domains are subset of R, the set of real numbers, and ranges are three-dimensional vectors. This means that for every number t in the domain of R, there is a unique vector in V3, denoted by R of t. If f of t, g of t, and h of t are the components of the vector R of t, then f, g, and h are called the component functions of R. And we write in this way. The vector function R of t is written as a vector with components f of t, g of t, and h of t, which can also be written by using the standard basis vectors. F of t times I plus g of t times j plus h of t times k. We will use t to denote the independent variable because it represents time in most applications of vector functions. Let's consider an example. If R of t, the vector function, has components t cubed, natural log of 3 minus t, and square root of t, then the component functions are f of t as t cubed, and g of t is the natural log of 3 minus t, and h of t equals square root of t. The domain of the vector function R consists of all real numbers t for which every component function is defined. Here, f is defined for all real numbers. G is defined for all t such that 3 minus t is positive because the natural log is defined for strictly positive real numbers. Thus, t has to be smaller than 3. And finally, h is defined for all non-negative t values. Therefore, the domain of R is this set, which is an interval. It takes 0 to 3, where 0 is included in the interval, but 3 is not included. Limits and continuity. If R of t, the vector function, has the component functions f, g, and h, then the limit of the vector function R is defined as follows. The limit of the vector function R of t as t approaches a is a vector whose first component is the limit of the first component of the vector function as t approaches a, and the second component is the limit of the second component of the vector function R. Similarly, the third component of the limit vector is the limit of the third component of the vector function R, provided the limits of the component functions exist. Let's have a look at an example. If R of t, the vector function, is defined as in the previous example, then the limit of the vector function r as t approaches 2 is the vector with these components. The first component is the limit of t cubed as t approaches 2, which gives us 8. And the second component is the limit of the natural log of 3 minus t as t approaches 2, which gives the natural log of 1, which becomes 0. And the third component of the limit is the limit of the square root of t as t approaches 2, which gives us the square root of 2. A vector function r is said to be continuous at a if the limit of the vector function r as t approaches a is equal to the value of the vector function at a, as shown in equation 4.1.2. In view of the definition 4.1.1, a vector function is continuous if and only if its component functions are continuous. For example, if r is the vector function with components as in the previous examples, then the vector function r is continuous at 2, since every component function is continuous at 2. Namely, t cubed is continuous at 2, natural log of 3 minus t is continuous at 2, and the positive square root of t is also continuous at 2. So the vector function r with these three components is continuous at 2. Properties of limit. Suppose u and v are two vector functions that possess limits as t approaches a and c be a constant, then the following properties hold true. The limit of u of t plus v of t equals the limit of u of t plus the limit of v of t as t approaches a in every case. In short, this says the limit of the sum of two vector functions equals to the sum of the limits of those vector functions. The second property reads the limit of the scalar multiple of the vector function u, which c is the scalar, as t approaches a, then it is exactly the c times the limit of the vector function u, just like the real valued case. Similarly, we have the product rules for both the dot product and cross product. The limit of the dot product of these two vector functions u and v is exactly equal to the dot product of the limits of those vector functions. Similarly, D reads the limit of the cross product of two vector functions is exactly equal to the cross product of the limit vectors. Let's try to prove A. Let u of t is a vector function whose components are u1 of t, u2 of t, and u3 of t. These are scalar valued functions. Similarly, the vector function v of t has components v1 of t, v2 of t, and v3 of t. They are the scalar valued functions. And since the limits of these two vector functions exist, we have the limits of each of these scalar valued functions. The vector with first component as the sum of the first components of u and v. Similarly, the second and third components are the sums of the second components and the third components of the vectors u and v. Now, by the equation 4.1.1, if we apply the limit the left-hand side, the right-hand side would become exactly this expression as written in equation 4.1.3. Since for the scalar functions u sub I and v sub I, where I stands for 1, 2, and 3, the limit of the sum of two scalar functions is exactly equal to the sum of their limits. Therefore, the equation 4.1.3 can be written as the sum of two vectors as shown, where the first vector is exactly the limit of the vector function u, and the second vector here is the limit of the second vector function v, as shown here. So we proved the limit of the sum of two vector functions exactly equals to the sum of their limits, just as in the case of the real valued functions.